Welcome to This Explainer. Today, we're uncovering how that simple navigation app on your smartphone actually relies on some seriously mind-bending cosmic physics just to function. We all use GPS pretty much every single day, right? Whether it's to find a new coffee shop or navigate a massive cross-country road trip. But most of us are completely unaware of the absolutely incredible science making it all possible behind the scenes. So, what does your phone's map app actually have to do with Albert Einstein? Well, let's dive right in and see how our mundane daily commutes are actually a continuously running, planet-wide validation of Einstein's theories of relativity. I know, it sounds totally absurd. What could abstract theories of space and time from over a century ago possibly have to do with that little glowing blue dot on your screen? As it turns out, absolutely everything. If we were to just completely ignore relativistic physics, your GPS would accumulate over 10 kilometers of error every single day. Just think about that for a second. After a single day of uncorrected operation, your car's navigation system wouldn't put you on the highway. It'd probably put you right in the middle of a lake. To understand how engineers prevent this navigational disaster, we really have to look at the beating heart of the GPS system itself. Section 1. How GPS tells time. To get why these crazy errors happen, we first need to look at how the system fundamentally works through highly precise timekeeping. You know, your phone doesn't just magically know where it is. It actually figures it out by acting like a super advanced stopwatch. It measures the exact arrival time of electromagnetic signals sent from at least 4 different satellites orbiting way up there, 20,200 kilometers above Earth. Because these signals travel at the constant speed of light, the system uses the tiny time delay between when the signal was beamed out and when your phone received it to calculate the exact distance to each satellite. But here's the catch. Because light travels insanely fast, we're talking about 300 meters in a single microsecond, the timing has to be absolutely flawless. A measly 3 nanosecond error translates to being a full meter off on the ground. Because of this, satellites have to maintain a perfectly synchronized coordinate time. This relies on a network of clocks operating in what physicists call a non-rotating local inertial frame. That essentially means treating the space around Earth as a perfectly still, unmoving stage just to make the math work. The atomic clocks out in space and the receivers down on the ground must tick in absolute unison. But keeping time perfectly synchronized across the vacuum in space and the surface of Earth, well, that is incredibly difficult due to the strange nature of physics. Section 2. The Cosmic Tug of War. The crucial point here is that time is not absolute. Instead, it's actively being stretched and compressed by a massive cosmic tug of war between speed and gravity. Einstein taught us that the rate at which a clock ticks depends entirely on its state of motion and the gravitational field it sits in. It's essentially a battle between the runner's clock of special relativity and the mountain dweller's clock of general relativity. For a GPS satellite in orbit, both of these factors are actually pulling the flow of time in completely opposite directions. Section 3. Speed, the runner's clock. Let's look at our first contender in this tug of war, the sheer, massive speed of those orbiting satellites. If you look at a moving reference frame, a moving clock actually beats slower than a stationary one. This is the core concept of special relativity, which Einstein introduced back in 1905. Because the speed of light is constant for everyone, time itself has to bend to accommodate moving objects. And GPS satellites aren't just calmly floating up there, they are hurtling through space at nearly 14,000 kilometers per hour. So, relative to us standing stationary on the ground, their onboard atomic clocks experience some extreme time dilation. Due to this immense speed, special relativity dictates that the satellite's clock is going to tick slower, literally losing 7.2 microseconds every single day compared to a clock resting on the ground. Now, I know, 7.2 millionths of a second sounds entirely microscopic to us, but to a GPS receiver relying on the speed of light, that is the difference between arriving right at your destination and being miles off course. Section 4. Gravity, the mountain dweller's clock. Now, let's see how gravity fights back against speed. About a decade after special relativity, Einstein dropped general relativity on us, which described gravity as a curvature in spacetime. Imagine an accelerating rocket thought experiment. It totally brings his principle of equivalence to life. It proves that clocks deep inside a strong gravity well have to work way harder to tick, so they run slower. Conversely, clocks in a weaker gravitational field tick faster. Our GPS satellite is kind of like a mountain dweller looking down at Earth. It's orbiting far above our planet's deep gravity well. Because the satellite is orbiting roughly 20,200 kilometers above the Earth, where gravity is vastly weaker, general relativity causes time to flow more freely for it. So the satellite's clock will actually gain 45.7 microseconds every single day compared to a clock down here on the surface. To recap, time is simultaneously being slowed down by the satellite's blistering speed and sped up by its really high altitude.
Section 5. The winner of the tug of war. All right, it's time to tally the score and see which physical force wins this daily battle of time manipulation.
When we combine these two wildly different effects, the math clearly shows a net gain of 38.5 microseconds a day. General relativity, that mountain dweller's clock, is the undisputed winner of the cosmic tug of war. The satellite clocks naturally run fast compared to ours. So to fix this, engineers literally have to apply a factory frequency offset. They manufacture the atomic clocks to tick slightly slower here on Earth. They intentionally break them, so to speak, just so they'll run perfectly once they're launched into orbit and sped up by the weaker gravity. Surprisingly, there's actually a fascinating sweet spot. If a satellite orbited at an altitude of exactly 3,186 kilometers, which is roughly half the Earth's radius, the time-slowing effect of its high speed would perfectly cancel out the time-speeding effect of its weaker gravity. At that magic altitude, the net relativistic effect would be zero. But our GPS system relies on a much higher altitude to maintain a wide line of sight, meaning it operates firmly up on the high ground where gravity reigns supreme. Section 6. The Sagnac complication. Right when you think the physics problem is completely solved, we have to introduce the final boss of this explainer, the Earth's rotation. This is where the Sagnac effect throws a massive wrench into things. While the signal is traveling from the satellite down to your phone, the Earth is continuously rotating. This means your receiver is actually moving during that tiny fraction of a second it takes for the light to reach you. Observers on our spinning Earth have to apply a Sagnac correction to account for this extra distance the signal has to travel to catch up with the moving receiver. If we don't account for this rotational area, our perfectly synchronized clocks immediately fall right out of sync again. And there's one more beautiful planetary quirk. Because Earth is rotating, it actually bulges out at the equator, flattening slightly into a shape called a geoid. Clocks closer to the equator move faster due to the Earth's spin, which slows their time down. But because of that bulge, they're also slightly higher up in the gravitational field, which speeds their time up. Remarkably, across mean sea level all over the globe, these relativistic effects perfectly compensate for each other. Nature's way of balancing the scales. Section 7. Conclusion. So, what should we really take away from this intricate dance of time, speed, gravity, and planetary rotation? The GPS network really isn't just an app on a screen. Your everyday navigation is an ongoing, real-time test of the absolute most complex theories of the universe. Every single time your phone calculates a route to a restaurant, it is simultaneously proving that time dilation, gravitational frequency shifts, and the relativity of simultaneity are real, absolute features of the universe we live in. I really hope this explainer leaves you marveling at the incredible, completely invisible physics that makes our modern world possible. The next time you pull up a map, just take a brief moment to appreciate that you are holding a receiver tuned to the very fabric of space and time. So next time you ask your phone for directions, will you remember the cosmic tug of war happening right there in your pocket?